Flange here. Hello, calculus students. This is the first part of section 1.1. Now, first we want to talk about relations. Functions are a kind of relation. A relation is any set of ordered pairs. Anytime you do a mapping or set of ordered pairs like points and coordinates and so forth, that's a relation. The domain is considered the input, what goes into the function. Usually those are x variables. And the range is what comes out, the output, y variables. Now, a function specifically is a relation in which every element of the domain is mapped to exactly one element in the range. That's a function. That's our formal definition. And we're going to see in class how this relates to many different ways of looking at a function in terms of the vertical line test and things like that. Now, in class, we did a little survey. We did what we call the birth month relation. Lots of people's birthdays here, lots of people's names mapped to their months. Notice in this case, February and looks like October were actually not part of the range, the output. So it's actually only 10 birth months in this case, and like 20 people's names here. In the other class, we had fewer people, but we had a lot of missing months. But this is what bothered some students, is that some people were going to the same month. Patrick and Colleen here going to March. Shiloh and Cassie going to May here. In the other class, Lane and Flange both going to September. Here we go. Graham and Will both going to July. Do these things make it not a function? So is the birth month function a relation? Is the birth month relation a function? Finally, the answer is yes. Because every element in the domain goes to exactly one element in the range. So even though we might have Flange going to September and Lane going to September, that's okay, because they're both going to exactly one element in the range. If Lane tried to break off and give us another month here, then that would not be a function. Now, before we get into functional notation though, let's just look at another way of looking at functions. And that's telling if you've got a function from the graph. So if I've got a function and it looks like this, is this a function? Well, the answer is yes, and we can tell just from looking at it by something called the vertical line test. And let me write that down for you. Okay, here we go. The vertical line test. If any vertical line crosses a relation more than once, then it is not a function. And it's not a function. And so we can go back up here and start looking at some vertical lines. Let's make some vertical lines here. And notice they're only going to cross it once. So therefore, we can imagine all the possible vertical lines, and none of them are going to cross it more than once. So therefore, it is a function. So this is a function. Now, how about this? You've just got the ordered the points 1, 1, 1, 2, 2, 2, 2, 3, and 3, 3. Is this a function? Well, by the vertical line test, no. No. Because we've got some points here, a vertical line that goes through. It doesn't matter that all these other vertical lines miss it or only go through once. These two, that's what ruins it for you there, is that they go through 2 points. And we can also see this on the mapping. 1 goes to 1. 1 also goes to 2. And when you see that diverging in the mapping, one element in the range, domain going to 2 elements in the range, then it's not a function. 2 goes to 2, see, that's okay. But 2 going to 3, again, we see that splitting off. That's not good. And 3 goes to 3. So it's the splitting off of a domain element into 2 range elements that makes it not a function. Now, another note is getting used to this notation of f of x. That's functional notation, and it's used to basically quickly show the rule for a function. So let's say f of x equals 2x plus 3. Notice I'm saying f of x. It's spoken this way. F of x. To represent the idea that this is not multiplication. It's functional notation. This point is going into a function. So you don't think of this as multiplication. So for f of negative 1, we have 2 times negative 1 plus 3. And you get negative 2 plus 3. That's 1. F of 5, plug 5 in wherever you see an x. 2 times 5 plus 3. 10 plus 3. It's 13. F of k. Well, wherever you see an x, we put a k. 2k plus 3. We're done. You get an expression for an answer. Now finally, f of x plus h. Put x plus h in where you see x. Don't just add an h on the end here. The x plus h has to go in where you see the x. So twice the quantity, x plus h, plus 3. I replaced the x with x plus h. So now simplifying, that's 2x plus 2h plus 3. We're going to do a lot more with this with our difference quotient tomorrow. But for right now, keep that in mind. Piecewise functions are functions defined in pieces. Look carefully at the stuff on the right, because these are the conditions for when this applies. So in this case, we actually have a couple of parts of our graph here. F of x equals 1 minus x squared for x less than or equal to 2, and f of x equals x minus 1 for x greater than 2. So when we make our xy chart to analyze things, you really want to look at this boundary between the two conditions. What's going on at 2? Well, when we put 2 in, we should put it in this formula. So that's 1 minus 2 squared. So that's 1 minus 4. That's negative 3. When we put 2 into this formula, though, we get 1. And this is definitely a line. This is a parabola. A parabola that when we put 0 in, we get 1. But now when we start going beyond 2, like with 3, we're going to put in the other formula. That's 3 minus 1, which equals 2. See, this when we put 0, we get 1 minus 0 squared is 1. So we're using the 1 minus x squared formula for points 2 and to the left, but the x minus 1 formula when we're at the points 2 or greater than 2. So when we graph this, we've got our points 0, 1, 2, negative 3. Looks like 1 goes to 0. And this is a parabola of the vertex at 0, 1. So we get a parabola on this side. Stop. Don't put the arrow there. Because now from then on, it turns into a line. 2 goes up to 3. Sorry. When you put 3 in, you get 2. When you put 2 into this rule, you get 1. 2 goes to 1, but we put an open circle there. Because we only get the half line. We only get a half line in this part. We only get part of a parabola over here. And that's what happened with the pieces here, forming sort of a disconnect between these two parts of the piecewise function. Now, to try this on your TID9, you go to your y equals menu, and under y1, go 1 minus x raised to the 2, and then put the big width symbol down. This is this big, tall vertical bar you see to the left of the 7. This is the conditional bar. That stands for width. And here's the condition, x less than or equal to 2. Type it in there like that. Now notice your less than symbol is above the 0. The less than symbol is above the 0 in the calculator. To get less than or equal to, you can just hit, to get this less than or equal to, you can just hit the gold key and then the 0 key. If you just hit the blue key, the second key, and then the 0 key, it gives you strictly less than. To get less than or equal to, hit the diamond or gold key on the left there, right below the second key, and hit the less than symbol. For y2, that will equal x minus 1 with, put that big with symbol that you see to the left of the 7 there, x greater than 2. And the greater than symbol is above the decimal point. And use the blue second key to get to the greater than symbol. Okay, you try graphing that while I go ahead and get a picture of this from GeoGebra. Here's my result from GeoGebra. You should be getting something similar on your TI9. Did you notice that when it was drawing it, it started drawing the parabola, and then it stopped for a while, and you had to wait a while. And then finally it draws this ray, this part of the line. That's because when the TI-89 goes through it, it actually uses this function and constantly tests to see if the x you want to use is this condition, is less than 2. So that's why it started right away. But then it kept trying to draw this even after 2, constantly coming back with false for this. And then when it started doing y2, it didn't draw anything for a while because it kept on looking at x minus 1 and then testing to see if the x was greater than 2. So that's why there seems to be that delay when you're graphing that. All right, best of luck with this. Flange out.